Alrighty. So now we're going to go on to section 1.5, A. We won't get all of 1.5A done, but we'll just see how far we can get it. Polynomial functions and complex zeros. Here's the good news about today's material. You learned it all in Algebra 2 Honors already. That's the good news. No new knowledge today. You know, dusting off some knowledge. I'm sure you've forgotten some of this stuff, but no new knowledge today. Polynomial functions, you know, spaghetti graphs, and complex zeros. That's right. Our old buddy I is showing up. We know how to find the principal square root for any non-negative real number. You might not have known that's what it was called. But if you say, what's the square root of 16? The answer is 4. Not plus or minus 4. No, it's just 4. Square root of 16 is 4. That is called the principal square root. Now, in earlier courses, like Algebra 2, we explored how to find the square roots of negative numbers. When the value of a radicand is negative, the radicand is something underneath a square root. Well, actually underneath any radical, but these notes are specific to square roots. That root is said to be an imaginary number. Imaginary number I is defined as the square root of negative 1. So we say the square root of negative 1 is the imaginary unit I. Just so we're clear on this, imaginary numbers are not made up. Imaginary numbers were discovered. They are simply a value that we have trouble comprehending. Therefore, we have to give it a symbol rather than an actual number that you know of. But how could you possibly give this thing a number on the real number system when it clearly is not itself a real number? It just doesn't work that way. And just so you know, mathematicians had decided on using the letter I for this, and then later on some people jokingly were like, oh yeah, because they're imaginary, and then the name just kind of stuck. It's not because they're made up, okay? They are two-dimensional numbers. They do not exist on your standard one-dimensional number line. They're not on there. They're off of it. But they are numbers and they hold value. And if you're curious, there's a great YouTube playlist called The History of I think it is, or The History of Imaginary Numbers. One of the two. I can't remember exactly what it is. It's great, especially the first 2 or 3 episodes. They really do a good job of showing you with pictures what this is. At one point in time, the guy grabs a graph, pinches it with his fingers, and pulls, and it lifts up off the paper in 3 dimensions. It's really cool. It was a fantastic visual representation of what they do. Anywho, let's recall how to do this. The square root of negative 9. That can be thought of as the square root of 9 times negative 1. Well, the principal square root of 9 is 3. And the symbol we use to represent the value of the square root of negative 1 is I. Therefore, the square root of negative 9 is 3I. So if I say, what's the square root of negative 16? You would say 4I. You would never leave a negative symbol inside a square root bar. It will always come out as an I. There it is. A complex number is any number in the form a plus bi. This is called standard form, and your complex numbers must be written in this order to be considered correct. They are not correct if they are out of order. A plus bi. Mr. M, is this always a plus? No, sometimes it's a minus, but that's because b could be a positive number or a negative number. What is A? A is the real part or real component of our complex number, where b is the imaginary part or imaginary component of our complex number. If you were not my student last year, you didn't hear this mind bomb, but here it is. All real numbers are complex numbers. All real numbers can be written in this format. Like the number 5. Here's the number 5 in its complex number format. 5 plus 0i. That is the number 5. So all numbers are complex numbers. All of them. At least all the numbers that you know of. We just don't always write the imaginary component if it doesn't exist. Because that one doesn't, it lacks a second dimension. So it's right on the number line. Here, we have the fundamental theorem of algebra. This is a lot of fancy talk for basically saying the degree of a polynomial is the number of complex zeros that polynomial has. So if your polynomial has 5 complex zeros, because it's a degree 5 polynomial, the fundamental theorem of algebra says I could factor it into 5 factors. That's all that says. So whatever the degree of your polynomial is, that's how many zeros it has. Now some of those zeros may be repeated, and that's multiplicity. She asked earlier about multiplicity. If your 0 is repeated, it's multiplicity. Number 1 says to factor this thing completely. It doesn't say solve for x. It says to factor it completely. But in order to factor it, we kind of need to be able to find the solutions. But first, what's the very first thing you look for anytime you're factoring anything? GCF. Yeah, we got to pull a GCF. This one has one. It's got a GCF of x. Gives me x squared minus 6x plus 13, and I'll be dag-nabbed if that quadratic doesn't factor. Shucks. How do we find the solutions of a quadratic that doesn't factor? The quadratic formula, or completing the square. I imagine most of you would want to use the quadratic formula though, right? Okay, and that's what we'll do. Here's the quadratic formula. Okay. The last thing that you need to do before you start using this thing is identify a, b, and c. A is 1, so that's what's in front of x squared. B is negative 6. And c is 13. Boom. Time to do our quadratic formula. X equals negative 6. That's positive 6. Plus or minus square root of. B squared, that's negative 6 quantity squared, that's 36. Minus 4 times 1 times 13. Card players in the room will instantly know what 4 times 13 is. 52, good. Oh, I wrote 2a instead of 2 times 1. Sorry. That's supposed to be a parenthesis. 36 minus 52. Well, that's negative 16. It's almost like I knew we were going to have to do the square root of negative 16 in my notes when I mentioned it earlier. Because the square root of negative 16 is 4i. So you have 6 plus or minus 4i over 2. And since both those numbers can be divided by that 2, they both need to be divided by that 2, giving you 3 plus or minus 2i. And these are your solutions. These are solutions. In order to write this as a factored polynomial, you have to remember that when factoring or when solving, don't worry, I'm going to bring this back up in just a second, okay? I'm just going to come over here and make a quick example. Let's say I set this quadratic equal to 0 and I said solve by factoring. You would get x plus 2 times x plus 3 and you would get 0. So what are the two solutions then? What's the solution from here? Negative 2, and what's the solution from here? Negative 3. The real reason why you have to say the opposite symbol as what you see there is because in all actuality, when something is factored, it says x minus the solution. That's why. This is actually x minus negative 2, x minus negative 3. It always says x minus the solution. So I have to do x minus these two solutions. So here we are factored. The green stuff is equivalent to this green stuff. The x on the outside, by the way, when you have an x on the outside, the solution for that is always 0. The first factor is x minus a solution. solution of 3 plus 2i. Then the other factor, x minus the other solution, x minus, nope, 3 minus, excuse me, 3 minus 2i. Now, could we distribute the minus sign? We could. You don't have to, but you can. You could call that x minus 3 minus 2i and x minus 3 plus 2i if you wanted to. Wouldn't make a difference. This is just if you don't like to see parentheses inside your parentheses. I just distributed the -1. There, and then there. Whatever. Yes? Yeah, because we're factoring, it has to say x minus the solution. The solutions are 0, 3 plus 2i, and 3 minus 2i. But this is the linear factorization. And it's linear because none of the x's have powers on them. Okay, yes?
So if you multiply all that now, you get the original.
Yeah, if you multiply all this is what you'll get.
All right.
Yeah, ask.
So isn't 3 minus or 3 plus 2i x?
That's one of the solutions, yeah. Because look, if you plug in, look. If you plug in 3 plus 2i right here, what is 3 plus 2i minus 3 plus 2i?
0.
0, exactly. And 0 times this is 0. That's why 3 plus 2i is a solution. When you write something as factored out, it's always x minus the solution.
Even if it's also
Look, x, what do you mean even if it's also x?
3 plus 2i what x is equal to?
Only if you're looking for when this quadratic equals 0.
Okay.
But this cubic equals 0. But we only did that so we could write it factored. X is any number x wants to be. The domain for this is all real numbers. This just happens to be the 0 and these two numbers. These happen to be the 3 solutions of the polynomial, meaning x equals 0, x equals 3 plus 2i, or x equals 3 minus 2i. Any of those 3 numbers when plugged in will get us 0 as a result. Which is why we call solutions zeros. Isn't that fun? Factoring something across the complex numbers. Let's do it again. This one has a GCF of y. Let's pull that y to the outside, leaving me with 4x squared plus 25. You know, if it had said 4x squared minus 25, this would have been a special case. Maybe you remember your special cases from Algebra 1 and Algebra 2. The difference of two squares? That a squared minus b squared always instantly factors to a plus b times a minus b. Maybe you remember that. Be nice if you did. And you might even remember your teacher, especially if they were me, saying that the sum of two squares never factors. Maybe you've been told that. Well, I mean, that's not completely true. It doesn't factor in the real number system. But the fundamental theorem of algebra says that a polynomial of degree 2 has 2 factors, 2 solutions. And I should be able to write this thing in a factored format. So a y on the outside of 2 sets of parentheses. So how do we do it? You know, 4x squared is a perfect square. And 25 is a perfect square. So, you know, I'm going to force it to fit this setup. There we go. And since we had the ability to take the square roots of negative numbers, this now says a perfect square minus a perfect square. Yes, Max? Instead of saying parentheses inside of parentheses, I use brackets inside of parentheses. But it means the same thing. It just looks nicer. Notice when you factor this way, both these parentheses have the square root of the front. You see that? They both have the square root of this at front. And they both have the square root of this at the back. One has a plus and one has a minus. So let's do that. Here's the y. Here's my parentheses. One has a plus, one has a minus. All right. A is the square root of a squared. So I need to know what the square root of 4x squared is. It's 2x. Whoa, just threw my pen. So there's a 2x at the front of both of these. And what is the square root of negative 25? 5i. There. It's factored. How about that? So I forced the sum of two squares to look like the difference of two squares, so it factors to a plus b, a minus b. And there's a vocabulary word for things in this setup, where all you did was change the symbol in between two terms. They're called conjugates. Hey, look at this box. It's got the word conjugate right there. If p of x is a polynomial with rational coefficients, then the irrational roots of p of x equals 0 occur in conjugate pairs. The irrational roots occur in conjugate pairs. What that means is, if you see that a plus the square root of b is one of your solutions, then so is a minus the square root of b every single time. They occur in irrational conjugate pairs. And using the exact same logic, if a plus bi is a solution, then so is a minus bi. These are called conjugate, irrational conjugates. Are here, sorry, these are called complex conjugates. There we go. Having trouble getting tired. Irrational conjugates, complex conjugates. Yes?
Does it make them irrational because it's subtracting?
The irrational is because it's a square root of something that you can't take the square root of. Like 1 plus the square root of 2.
But it's also
No, this is complex.
oh.
These are irrational because they have a square root of a number. These are complex because they have an I in them. Somebody last period realized that they changed the vocabulary. It says if a plus the square root of b is a root, then a minus square root of b is a root. If a plus bi is a 0, then a minus bi is also a 0. And they realized that the vocabulary changed from root to 0 and wanted to know what the difference was. The difference was a root is a number where your graph will cross through the x-axis. A 0 is a solution. That means you'll get 0 if you plug it in. But it can't be a place where the graph crosses the x-axis if it has an I on it, because they're not on the x-axis. They're off of the x-axis. That's the difference. So when you say a solution, a root, a 0, an x-intercept, all four of those things mean the same thing for real numbers. However, complex numbers cannot be x-intercepts. So they cannot be roots, but they are still solutions, also known as zeros. Yes?
So if you plug in
A complex number, yeah.
like you graph that
You graph a polynomial, yeah.
has like a root like that.
It has imaginary roots, yeah.
It's never,
Well, imaginary zeros,
yeah, it's not gonna touch the x-axis.
not where those numbers occur, no.
Okay.
But you're going to see what they do to the graph in just a moment. Is that a question for me over there, Hunter, or no? Okay. A polynomial, oh, whoops, I forgot. Corollary. This means this follows directly because of this. A polynomial function of blank degree with real coefficients has at least one real zero. What is the only way that I can guarantee my graph is going to cross through the x-axis? It has to do with the end behavior.
Oh, it's like x to the third.
And x to the third does have a solution. But why does that have to have a solution? It's got an odd degree, yeah. So what does it tell you about its endings? They go opposite directions. So, oh, a polynomial function of odd degree with real coefficients has at least one real solution all the time. So any graph that has an odd degree is guaranteed to have at least one real solution. That's what a real zero meaning a real solution, one x-intercept. Could have more, but you're guaranteed to have at least one. But that's not true for even degree polynomials because their endings could point in the same direction and then never touch the x-axis. A polynomial function f of degree 5, whose coefficients are real numbers, has these three zeros. But the fundamental theorem of algebra tells us a degree 5 polynomial has to have 5 zeros. So I wonder what the other two are. Well, complex solutions always come in conjugate pairs. So if positive 3i is a solution, so is negative 3i. Think of this as being 0 plus 3i. Here's 0 minus 3i. And if 1 plus I is a solution, bless you, so is 1 minus I. You see, when you do conjugates, all you do is change the symbol in the middle, and that's it. It's a place where the graph touches the x-axis. So what you have here is a degree 5 polynomial that interacts with the x-axis exactly one time and never again. The only time it ever deals with the x-axis is at x equals 2. It never touches the x-axis again. Yep.
So -2 wouldn't be answered?
No. Real solutions don't have to come in conjugate pairs. The only solutions that have to come in conjugate pairs are irrational, like these, or complex. All right. Find a polynomial function of degree 4 whose coefficients are real numbers and that has these three zeros, a 2, and a negative 3 plus I. But here's the thing. That's only 3 solutions, and I know for a fact, because the fundamental theorem of algebra tells me so, there must be 4 solutions. But one complex solution is impossible. So there is another complex solution. At x equals its complex conjugate of negative 3 minus I. So now that we know our 4 solutions, we can write this thing factored and then do all the multiplications to get it back into standard form. Yes? Is that a question? You just scratching your face?
I was going to ask a question and I answered it myself.
Okay. Where's my pen? There it is. Here we go. F of x equals. We know, oh, by the way, it says a equals 1. That means the leading coefficient is a 1, so I don't need a multiplier on the front of this. I know that 2 is a solution, so I know that x minus 2 is one of my factors. Oh, actually, it's one of my factors twice. That means the graph bounces at x equals 2. That's what that means. And then I've got this. X minus negative 3 plus I and x minus negative 3 minus I. Ew. Got to do all this foiling. X minus 2 quantity squared, that means x minus 2 times x minus 2. This is AP Precalc. By now, I expect you to just be able to FOIL like this in your head. X squared minus 4x plus 4. It's literally double this number and square this number. That's all it is. And to tell you what, this would kind of suck, wouldn't it, if you were going to distribute all this stuff? You'd end up with foiling inside of foiling, wouldn't you? Yuck. Tell you what. I'm going to distribute the negative sign. And then I'm going to show you this. You see how they both have an x plus 3 at the front of them? And they both have an I at the back of them? Sure looks to me like an a minus b times a plus b situation, which will always get you that. Square the front, square the back, put a minus sign in between. Square the front, square the back, put a minus sign in between. And the same way that I foiled this, I expect you to do it here. Double the 3, square the 3. Double the 3, square the 3. Now minus I squared. So if I is the square root of negative 1, what is I squared equal to? Negative 1. So we have successfully rebuilt the quadratic that produces those two complex conjugate solutions. And then there's lots of distributions and combining like terms. Does everybody in the room know how to distribute and combine like terms? Fantastic. So rather than waste our time doing that, I'm just going to write down what you get when you do that. X to the 4th plus 2x to the 3rd minus 10x squared minus 16x plus 40. There is the polynomial that has those 4 solutions. The hardest part was rebuilding the quadratic. Now let's graph this on our graphing calculator. Go to y equals. And the reason why is because it says analyze the characteristics. That means maximums, minimums, increasing, decreasing, that kind of stuff. X raised to the 4th plus 2x raised to the 3rd minus 10x squared minus 16x plus 40. Now I'm not going to hit graph. Instead, I'm going to adjust my window so that it fits this picture perfectly. Window is right here. Boop. Window. Right there. And notice that the x's go from negative 5 to positive 4. And they count by ones. Notice that the y's go from negative 10 to positive 60. And they count by tens. And don't worry about x res and delta x. You won't ever deal with those. Or trace step. Don't worry about that. Your calculator will set those numbers for you. And then I hit graph. Now, just a minute ago, who was asking me about that the complex answers are places where it doesn't hit the x-axis? Yeah. And I said you would see what they do. So here's the place where your graph touches the x-axis at x equals 2. If I were to shift this graph down, could I make it hit the x-axis a total of 4 times? Of course I could. If I shifted it down so that the x-axis went through, say, like right here, there's 4 answers, right? That's because there's 2 complex answers right here. So complex answers will create a wiggle in the graph that'll look somewhat symmetric because complex answers are conjugates. So it'll almost act like a parabola around the 2 complex answers. That's essentially what it does. Is it creates a tiny parabola somewhere that doesn't touch the x-axis. Cool beans? So now you know what they do. Okay. let us see. Well, we could see that that's at negative 2 comma 0. That's right here. Positive 2 comma 0, I'm sorry. That's right there. And then it goes up and to the right. Whee! Okay. Oh, look at that y-intercept. If you plug in x equals 0, you get 40. So that's perfect. It's not a maximum or a minimum, but at least it's a perfect point. Got to track down our maximum and our minimum, though. These two bad boys. So let's do maximum. Second trace. Maximum is command 4. Go to the left of it. Go to the right of it. Get in the middle. Negative 0.7-ish, comma, almost 46. So like here-ish? That feels good. And then I need to track down this minimum, second trace minimum. That's to the left. That's to the right. That's somewhere in between. Like negative 2 3/4, comma, almost 24. So here-ish. And then it does that. There. So it says to analyze. Rather than write the intervals, we're just going to write on the graph whether or not we're increasing or decreasing. This piece right here is decreasing. This piece is increasing. This piece is decreasing. And this piece is increasing. I'm hoping by now you already know how to find those places. We would have used brackets at those x values. But I'm going to call it there, nerds.